So, welcome. This is diffraction and polarization. So, okay, we know that when light goes through a pair of slits, you get interference. But what's not so obvious, but is also true, is that when light goes through a single slit, you can get these weird patterns where you get this shading effect. In fact, when light goes over a single edge, so there's not two edges, there's a single edge, you can get these things. Here's an image. I'm sorry, I always do this, don't I? Here's an image. So here's the light source, and here's an edge, like a razor blade edge. And if you look in detail, you can see that when you photograph what's going on at the edge, you get this series of fringes next to the edge. And that's a problem, you know. If you're trying to get very high resolution optics, that's going to mess with your optics. That's a problem. If you put light through a single narrow opening, this is a pinhole, you will get not a spot of light, but you will get these discs around. If my light source is a long, long way away from the screen, or I use a lens to fool my screen into thinking it's a long, long way away from the light source, I get this where you get true darknesses between these discs. And that's called Fraunhofer diffraction. And if I just do it where it's like, you know, here's my pinhole and here's my screen, I will get this, which is Fresnel diffraction. Okay? Just know those two names exist. You don't need to know any more than that. So we say diffraction is the bending of light when it passes an obstacle or barrier. We get diffraction from an abrupt edge, such as a straight edge. So frankly, in that last chapter, when we showed those diffraction patterns, those interference patterns, we were cheating a bit. We were taking the pattern from the middle of a more complicated pattern which showed diffraction effects as well. So anyway. Okay. We don't have two slits, we only have one. How can we mathematically analyze this? We can analyze it as if it were two slits. So what we do is we imagine having a top half and a bottom half. And we do the same trick we did before. We said, okay, it's going off in that direction to the top right, and we can imagine this path difference and all that kind of stuff. What we get is, from Huygens' principle, each portion of the slit acts as a source of waves. So light from one portion of the slit can interfere with light from another portion of the slit. Okay. If the slit is width A, then for destructive interference, m lambda equals A sine theta, where m equals 1 or 2 or 3 or 4. The light intensity pattern has a distinctive shape, and it's this shape. It's basically like that. Don't worry so much about that. Know it exists. Okay. Here's where it counts. I have a single opening, and I have two light sources. Let's say a telescope and two stars. Let's say a pupil and two headlights. Well, the red, if you got the colors on there, the red star sends light which passes through the pinhole and forms, again, not a little dot, but a dot with a series of rings around it because of diffraction. I can do a cross section through it and I get that little trace. Brightness in the middle, then a dark ring, and then a bright ring. The green star does the same. They're not on top of one another because the stars are coming at different angles. So I can easily see that there are two stars. It looks a bit more complicated than I expected. Not two dots, but now two dots with rings around them. But I can separate the two of them. Now let's imagine the stars are closer together. Can you see how I start getting to the stage where the light distributions start messing with each other? They overlap. And I'm showing this to some extent at the bottom, on this bottom diagram. On this left-hand diagram, we see two light sources that are easily resolved. And you can see there's no ambiguity there. There's two light sources. And then on the far right, we have two light sources, but they look like one. And then in the middle, there's two light sources, and you can tell there's two. We say that's just resolved. Now, this is a problem that's faced within many actually forms of analysis. You have two distributions, two light sources, or two peaks. You might have a peak that's associated with one type of ion going through a mass spectrometer, and you might have another peak which is associated with another type of ion going through the mass spectrometer. They're almost the same charge to mass ratio, so they lie on top of one another, but they're distributions. We know they're distributions. Can I separate them? How can I separate them? Sometimes in Auger electron spectroscopy, you'll get a distribution of electrons that have a certain energy, and you'll get another distribution with almost the same energy. The distributions are wider than the separation between the two energies, so they overlap. How do you resolve these things? How do you figure out? Is it one? Is it two? How much of one do you have? How much of the other do you have? There's a whole science in this, and you need rules. And what we say is that when a central maximum of one image, say the red central maximum, falls on the first minimum of the other image, well, there's the red maximum falling on the first minimum. The image is said to be just resolved. This limiting condition is known as the Rayleigh criterion. So when the crest of one falls on top of the trough of the other, the first trough of the other, you're just resolved. If they're outside, great. If they're inside, you can't resolve them. So it's a criteria we have. I'd like you to be able to look at these diagrams or these images and tell me which is well resolved, which is unresolved, and which is just resolved. And I'd like you to be able to tell me the Rayleigh criterion if I asked you for it. Okay? So, we can find a bit more detail about the Rayleigh criteria for a circular aperture or for a slit. And we can do some analysis. I don't care about the analysis. I'm not going to take you through the analysis. I can't remember the analysis, actually, to tell you the truth. But what I'm going to tell you is for a circular aperture, the system of diameter d, so that is for a circular aperture with a diameter d, the minimum angle, the angle between two things that you can just resolve, it's the minimum angle of resolution, is 1.22 times lambda over d. Lambda is the wavelength of the light, and d is the diameter. If the two things are separated by a bigger angle, we can easily resolve them. If the two things are separated by this angle, we can just resolve them. And if the things are separated by a smaller angle, we can't resolve them. So for any optical system, we can point to it and say, that's got a minimum angle of resolution. And if it's a narrow type of instrument like a pinhole, when D gets small, your angle gets big. What that says is that the minimum that you need to be separated by gets bigger as your telescope gets narrower for the same light. You want a nice high resolution image, get yourself a big wide telescope. You have a narrow telescope, yeah, you can magnify as much as you like, but you will not resolve detail, because theta min, the minimum angle of resolution, is big for a narrow telescope. You need things to be far apart to be seen as two things. And the minimum angle of resolution is small for a big telescope. So when you're looking through the catalog and you want high resolution, you go for a telescope which has a small theta min, because that's the angle that things have to be separated for you to see them as two things. Smaller the angle, the more detail you have on anything you look at. See what I'm saying? So this is one of these weird things where the better it is, the smaller the angle. The worse it is, the bigger the angle. And a typical telescope, it's measured, the theta min is measured in arc seconds. And degree is 1/360th of a circle. And an arc minute is 1/60th of a degree. And an arc second is 1/60th of a minute. So an arc second, 1 arc second is equal to 1/3600th of a degree, which is, I mean, it's nothing, it's tiny. And a good 8-inch telescope will have a really nice resolution like that. Notice, if I go to long wavelength light, which way am I going? If I go to long wavelength, am I going redder or bluer? Going redder. So radio waves. Radio waves are as big as mountains, or at least as big as rooms, kilometers measured in. Radio waves, massive landers, mean massive minimum angular resolution. Very poor resolution on a picture. So typically in astronomy, you'd see the optical image and you'd see this thing with all these sharp stars, and then you see the radio image with this blob, because it couldn't resolve anything. How do you get by that? If lander's going to be big, you make D big. Is that why radio telescopes are like dish-shaped and massive? Not really, actually. It turns out that's not really it. They're that size because they're dealing with big wavelengths, and you want to have kind of like a telescope which is of the order of the thing you're trying to measure, the wavelength of the thing you're trying to measure. But the real way you get much better radio telescope resolution is you take two telescopes that are miles apart and you connect them together. Now, that's like having a nice converging lens. Let me ask you a question. If I take a converging lens and somebody paints the middle out of it, and I look through it, what do I see? Will I see an image with a hole in the middle of it? No, because it bends the light. So it doesn't matter about the hole in it or the paint on it. I'm still getting the light I want. It's just it's not coming through the middle bit. So the intensity of the light decreases, but I'm still getting the same lens effect. So this is kind of really clever. It's like having a lens and I just threw away all the middle of it. But it still works. So this is like one edge of my telescope, and that's like the other edge of my telescope, and they're miles apart. So I've not increased my sensitivity, because it's still two little dishes, but I've really increased the resolution of the radio telescope. And they've actually even they've connected telescopes, for instance, in Puerto Rico and Hawaii, I think. Certainly California. I don't know what the two angles are, but as long as they're on the same side of the world, you can point them at the same sky. Now, they have to be, you can't just take data and then later on combine it. You have to combine it immediately, or you have to time index it so you can compare it. I'm not sure why that is, but it's not just taking two images and shoving it together. The detectors have to be time locked for this to work. But that comes out of there. It comes out of there. Good. And okay. So know that equation. Be able to use it. And clearly, if I asked you to plot me a graph of theta min versus lambda, get me a straight line, and theta lin versus versus the diameter, get me an inverse. Yeah. Okay. Yeah. If I say plot me a graph of theta versus d, then it's going to go like that. This theta. This is a great opportunity for me to ask you, other stuff. Give me a straight line, yeah. They're just background skills. Diffraction grating. Why stop at 2 slits? If I had 100 slits, I'd get more light going through it. The whole thing would work better. So people started off by taking a polished surface. What's a polished surface? Is it specular or is it diffuse? Polished surface, like a mirror. Specular. They took a specular surface and they took a grinding tool and they just put a whole series of lines down it. So they had this like little reflection. Then later on, they just started drawing a whole bunch of lines on a piece of paper and photographing it, and they'd used a 35mm slide. And now they just do it with computers. They just make a very thin, cheapo diffraction grating. They cost nothing. It acts like a whole bunch of slits. And what happens is, well, whereas before I had something that well, I cheated before. But whereas before I had this pattern of light and dark and light and dark and light and dark, I have the same thing, although it tends to be light and dark and light and dark. The light bits tend to be really very well defined. Same idea. M equals 0, and then M equals 1, and M equals 2. I'm so sorry, I've got my people I know are talking to each other and there. Oh, that's not to me. It's tax day today. My wife does taxes on the last day. She takes it as a point of pride. I always worry that. I said, go to H&R Block. She goes, I'm not going there. Oh, man. Anyway, so we say each slit produces diffraction, and diffraction beams interfere with each other to produce a final pattern. The condition for maxima in the interference pattern is, we've been here before, d lambda equals d sine theta equals m lambda. Agreed? We've had that before. It's the same old, same old. So now, let's put it in a machine. So we have a light source. We have the light goes in, and the red light goes in one direction, and the green light goes in another direction, and the blue light goes in another direction. So it's dispersing the light rather like a prism did, but it's much more efficient. We say consider two nearly, and I don't care about. So I want you to know about this instrument, and frankly, I don't expect you to remember this equation, so don't worry about that equation. Okay, but you can figure out the resolution of a system. Oh, okay. But there's a, how am I doing for time? 10 minutes, I can do it. We have a diffraction grating. Let's say that there are 600 lines per millimeter. Let's say a light comes through. Let's say we have 400 nanometer is the lambda. I want to know what angle we diffract at the first time. So, what did I just do? So this is first order blue, because blue light's first order. This is blue. First order blue. I'm using monochromatic light. I'm not using white light. I'm using monochromatic light. I say m lambda is equal to d sine theta. So sine theta is equal to m lambda over d, which equals, this is my first order. So m is going to be 1. And my lambda is 400 times 10 to the minus 9, because it's in nanometers, over d. I've got to work out what my d is. D is equal to 1 millimeter divided by 600, which equals 1 over 600 times 10 to the minus 3 meters. So 1 second EE to the minus 3, enter, divided by 600 equals. D is equal to 1.667 times 10 to the minus 1, 2, 3, 4, 5, 6. 10 to the minus 6, I think. Meters. 1, 2, 3, 4, 5, 6. Yeah. So this is 1.667 times 10 to the minus 3. 10 to the minus 6, I'm sorry. So sine theta is equal to 400 second EE to the minus 9, enter, divided by 1.667 second EE minus 6, enter. That's 0.2399. So theta equals sine to the minus 1 of 0.2399. So theta is equal second, whoops, go back, second sine, second answer. I'm not sure that worked out right. Second sine 0.23399. I'm getting, oh yeah, I'm in radians, yes. 0.236 radians. Yeah. And if I want in degrees, I can, change it to degrees. Makes no difference. That's how those spectrometers work. Now, added bit. E equals HF, which equals H lambda over C. E for this light is equal to H. Anybody remember what Planck's constant was? 6 point.
626 times 10 to the -23rd.
My word, you're doing better than I am. So that, and our lambda we worked out to be 400. Yeah. So our lambda is 400 times 10 to the minus 9 over 3 times 10 to the 8th, which equals, so let's have a look, 6.6 second EE to the minus 23.
It's actually minus 34.
34, okay, thanks. Yeah.
Is that Avogadro's number?
I don't know, maybe your teacher should know. 34 times 400 second EE to the minus 9, enter, divided by 3 second EE to the 8 equals, oh, that's ridiculous. I've done something wrong. Can anybody got a decent number for this? It's going to be, that's going to be 2, it's going to be 800 times 10 to the 34, that is, minus 34, minus 43, minus 8, minus, even lower, minus 50 something.
Are you sure it's lambda over C?
Lambda over C. H.
Isn't frequency 1 over?
V equals F lambda. F equals V over lambda. Oh. F equals V over lambda.
That would do it.
Of course. And so work out the answer. Oh, we're out of time. No. So that's going to be C, 3 times 10 to the 8 of lambda was 400 times 10 to the minus 9. 3 6s are 18, and a bit more makes 20. 20 over 4 is 5. That would be 5 times 10 to the minus 34, and 8 makes minus 26. Minus 9 on the bottom makes minus 15, minus 14, minus 15 joule, something like that. Can we check it? Something like that. In a lab, we're going to do a lab, and what you'd do there is you'd send some light in, you'd measure the angle of the colours, you'd figure out what the energy of those colours represent. In doing so, you would determine the energy levels for hydrogen using a piece of film that cost about 25 cents and a lamp which probably cost about $10. And you'd find this fundamental thing from the world. It's really quite nice. Leaves me one last thing. I can see we're packing up, so okay. I don't mind coming next time. We've got one more bit to do, so we'll call it a day there. Okay. I don't want to rush it because this is good test questions on this. Okay. So let's pause it there.